In this section of the text, we're going to talk about inverse trig functions and right triangles. For this section, you will need to recall the inverse trigonometric functions and their properties. So the three main ones to remember are your y equal arc sine of x, y equal the arc cosine of x, and y equal the arc tangent of x. And again, the properties that you're going to want to remember are their domains and ranges, and basically what is happening to the function over the interval. We are going to need these to solve right triangles as well as evaluate angle values. So for example, let's find the exact values for the functions. If the value cannot be given exactly, find the decimal rounded to 2 decimal places. Okay. So in this first example, we're looking at the arc cosine of negative root 3 over 2. So here again, our cosine inverse function is defined with a range between 0 and pi, which means our angle values are going to be between 0 and 180 degrees. Our reference angle for this is going to be a 30-degree angle, because we know that cosine of 30 degrees is going to give us a value of root 3 over 2. To make it negative, again, if we're looking between 0 and 180 degrees, we know that we're going to be in quadrant 2 in order for the cosine to be negative. So here, our arc cosine of negative root 3 over 2 is going to equal 150 degrees. Okay. If we're looking at the arc sine of negative 1, again, we're thinking, when does sine theta equal negative 1? Well, the arc sine is defined for angles between negative pi over 2 and pi over 2. So from negative 90 degrees to 90 degrees. We know that sine is going to be negative 1 at 270 degrees, or 3 pi over 2. So here, we basically need to find the quadrantal angle that is coterminal with 270 degrees. So the arc sine of negative 1 is going to be negative 90 degrees. For the arc tangent of 3, okay, this is not one of our nice values. So again, this means we are trying to find the angle when tangent of theta is equal to 3. Well, because it's not a nice value, not one of our basic functions, we are going to need to use a calculator. So here, you're going to need to find your inverse trig function on your calculator. And remember that tangent to the negative 1 is not the same as 1 over tangent. So if you try plugging that in, you are going to get a wrong answer. Here we actually need to find either the arc tangent button or tangent to the negative 1 button. So plugging in, we'll get 71.57 degrees. And again, make sure your calculator is in the proper mode. Radians if you're looking for radian measure, degree if you're looking for degree measure. And in this case, we wanted to round to 2 decimal places, so we'll round off to 71.57. In our last example for this one, we are looking at the inverse cosine of 2. And so again, this is basically saying that we want to find the angle when cosine of theta is equal to 2. Well, we know that cosine is always going to be between negative 1 and 1. Okay, so again, if we're looking at that arc cosine, it means those domain values have to be between negative 1 and 1. 2 is not in that domain, so this is just undefined. So there's the first reason we're going to look at some inverse trig functions. And again, this should be familiar from what we did with radian measure. The only difference here is that we use degree measure. Another use for our inverse trig functions is to solve triangles. Now up to now, we've had some fairly nice angles to work with. We had that table of all of our nice values between 0 and pi over 2 and all of our quadrantal angles, and if it was any of those, we knew exactly how to find the triangle. So now we're going to look at triangles that aren't so nice, meaning when I look at my trig function, sine, cosine, tangent, etc., it's not going to be those nice values 1/2, root 3 over 2, root 2 over 2. Okay, we're going to have to actually calculate them. Okay. Again, when we say to solve the triangle, we basically mean find all of the angle values and all of the side lengths. So in this triangle ABC, we were given side length C is 7, side length A is 4, and we have that C is the 90-degree angle. So we want to find angle A, angle B, and side length B. Okay. Now in a case like this, because I don't have the other angle values, I can't start by solving for the angles. So let's start by finding the other side. And here we can do that using the Pythagorean theorem because again it is a right triangle. So again we're going to plug in 4 for A and 7 for C, so we'll get 4 squared plus B squared is equal to 7 squared. Now we can just solve for B. Remember, for these solutions we don't need the plus or minus because we're just looking at lengths. The sign will come depending on what quadrant we're looking at if we're looking on the standard position angle. In this case, since we're just given the triangle, we just treat it as a length. So B is going to be the square root of 33. Now that we know B, we can start finding some of the other sides. Okay? So in particular, if I want to find angle A, for example, I can use the 4 and the 7, so we're looking at the opposite of A and the hypotenuse of the triangle, so we're going to be looking at the sine of A. From there we can go ahead and solve using our inverse trig function. Plugging into the calculator, we can see that A is going to equal 34.85 degrees. Again, round to 2 decimal places unless otherwise stated. So now we just need to find angle B, because we have all of the other information and we just want to finish solving the triangle. Well, angle B, we could do the same thing, and we could use the cosine of the angle, but in this case we've already got 2 of the 3 angles, and we know that the sum of the angles has to equal 180 degrees. So we can just subtract to get the other angle. So B will equal 55.15 degrees. So now we have all of the values for our triangle. And so there is our solved triangle. Now we can also use this information in our applications. Some of our applications, it's not necessarily going to say that I need to find the inverse trig function of a particular angle. So in this example, an observer views a space shuttle from a distance of 2 miles from the launch pad. We want to A, find the height of the shuttle in terms of the angle of elevation, theta, and B, if the shuttle is 20 miles up, find the angle of elevation. Now to do this, we need to talk a little bit about angle of elevation. Angle of elevation is usually the angle measured from the horizontal up to a particular height. So if we draw a picture in this example, we can see that from our space shuttle, 2 miles away from the launch pad is going to be where our observer is. And measuring from the horizontal up to the line of sight of the space shuttle is going to be our angle theta. H is the height the space shuttle is from the ground. Okay, so for part A, we wanted to find an expression for the height of the shuttle in terms of the angle of elevation. Well, here we can see we have the 2 side lengths, and we don't know the hypotenuse. So that tells me we're probably looking at a tangent or a cotangent function. Here, if we use tangent, we can say that the height is going to be divided by the 2 miles to give us the tangent of the angle. So to put this in terms of our height, theta, our height is just going to be 2 times tangent of theta. And there's our solution for part A. For part B, we actually want to find the angle of elevation if we know what the height is. So if the height is 20 miles, we want to figure out what that angle of elevation has to be. So here we can solve 20 is equal to 2 tangent of theta, and we want to solve for theta. So we can start by dividing out by 2 and looking at the arctangent of the angle. And then to get our value, we're going to just plug this into a calculator and again round to 2 decimal places. So our angle of elevation is going to be 84.29 degrees. Now one of the things to keep in mind when you're working with these word problems is that your angle of elevation is always what we consider an acute angle. In other words, when you're looking for angles of elevation or you're using those within problems, if you're getting a theta that is 120 degrees or 110 degrees, then you know you did something wrong. It is always measured up from the horizontal and it can't go past the vertical. Otherwise, we'll be looking at kind of the other side, an angle of depreciation instead of an elevation. So one of the other things you're going to be asked to do in this section is to solve basic trigonometric equations. In basic trig equations, you will be given a trig function and a value, and you'll be asked to find the angle. These are basic because at this point there's only going to be one trig value and one angle will be found using the inverses. Okay. Later we'll look at more complicated trig equations where maybe you have squares or roots or fractions or additions and subtractions of other trig functions, and maybe we'll look at multiple angles or reduced angles or things like that. But for now we're just going to look at some basic trig equations. Here's an example of a trig equation. Sine of theta is equal to root 3 over 2. And here we want to solve for theta values between 0 and 180 degrees. Now, all of your basic trig equations, there are of two types. Either you're going to be solving within an interval, or you're going to be solving for all solutions. For now, we're going to just start with those within an interval. Because again, those with all solutions, we have to consider some other things in addition to what we're going to do here. So in this case, to solve, I'm going to first begin by finding that angle theta. Okay? And we can almost think of it as a reference angle like we did before when we were trying to find values in other quadrants. Here again, I'm going to start with taking the inverse trig function of both sides and finding that angle theta. So again, using our properties of the inverse trig functions and the values of our trigonometric functions, we see that theta is going to be 60 degrees. Now, because we want the values between 0 and 180, we need to consider every place that sine is going to equal a positive root 3 over 2 in both quadrant 1 and quadrant 2. Okay? So we know sine is positive in both of those quadrants, and we have the reference angle, meaning the 60 degrees, so we just need to apply that to both quadrants. So in quadrant 1, our value is going to be 60 degrees. In quadrant 2, our angle is going to be 120 degrees. So let's look at another example. We'll do the same thing, but this one, let's look at one that doesn't have such nice values. Okay, because not all of the ones you're going to get are going to have our nice angles that we talked about in the unit circle and in the early triangle sections. So here, let's look at cosine of theta equaling 1/9 for theta between 0 and 360 degrees. So basically, we're looking at one full revolution of the unit circle, and we want to find the theta values that'll give us a cosine equal to 1/9. Okay. So again, we're going to start by looking at the inverse function. Again, because this isn't one of our nice values, we're going to need a calculator to evaluate. Okay. And again, we'll go ahead and round to 2 decimal places. So notice that this value is less than 90 degrees, which means it's in quadrant 1. If we're looking at one full revolution of the unit circle, then we know that cosine is going to be positive in both quadrant 1 and quadrant 4. So we need to find the value in quadrant 4 that's also going to have this as a reference angle. So to find that angle in quadrant 4, we're just going to take 360 degrees minus that reference angle of 83.62 degrees to get the 276.8. So our two values for theta are going to be 83.62 degrees and 276.80 degrees. Another concept that will be needed in calculus is to be able to compose trigonometric functions. When composing trig functions and trig inverses, it's important to remember the properties of the functions as well as the inverse functions, and it is useful to set up the right triangles to solve. Sometimes you're not going to be able to just look at the problems and solve them, and so oftentimes you're going to need to set up triangles to find relationships between the sides and the angle. So for example, we want to find the exact value of the expression sine of the inverse cosine of 3/5. So as we can see, this is a composition of a sine function and an inverse cosine. Okay? So to start a problem like this, we want to start from the inside and work our way out. By starting on the inside, it means I want to look at the angle, since it's an inverse trig function, that gives me a cosine equal to 3/5. But again, we can think of that as cosine of theta equals 3/5. And given that information, we can set up a triangle, because if I know what the cosine value is, I know two of the sides, and the theta is the angle that we're looking at. So we have our 3, 4, 5 right triangle. So now that we know what the cosine inverse is, meaning that theta value, we can now find sine of theta. So our sine of theta will be 4/5, which just means that our sine of the arc cosine of 3/5 is just 4/5. Now notice in this problem, we were able to find the value of the composition without ever having to find the value of theta. And in some cases, we need to be able to do that because our thetas aren't always going to be nice values, and in most cases, we're going to have to approximate them. And if we approximate and then try to evaluate something else on that approximation, we're going to get really bad answers. They're not always going to be exact. So here, if we can actually do it without finding an approximation for theta, but using the fact that it does relate in the triangle, then we can get exact values for the answers. Okay. So let's look at another one. Let's say secant of the sine inverse of 12/13. We want to find the exact value of that expression. Okay. So here we're going to begin the same way. We're going to look at the inside piece, and because it's an inverse trig function, we'll look at it in terms of theta, and then form our triangle. So if sine of theta equals 12/13, we can start our triangle this way. Again, using the Pythagorean theorem, we can solve for our other side length. So our triangle becomes a 5, 12, 13 triangle, and now we can find the secant of theta. So our secant of the inverse sine of 12/13 is going to be 13/5. Now in some cases you may not be solving, but just rewriting the expression. Okay, and the idea there is going to be the same. I'm going to use the triangles to figure out the relationship between the two expressions, the trigonometric and the inverse trigonometric, and then use that relationship to find the value. Okay, so here let's rewrite the following as algebraic expressions of x. And for this first one, let's look at tangent of the arcsine of x. Now if we start out the same way we just did, we're going to let sine of theta equal our x. So setting up our triangle, we see that we get one side is x, our hypotenuse is 1, and we just need to find the other side. So by the Pythagorean theorem, we can see that the other side is going to be the square root of 1 minus x squared. So from there, we can solve for our tangent. Our tangent of theta is going to be the opposite over the adjacent, so x over the square root of 1 minus x squared. And now that we have the value, we can go ahead and simplify it and write it back in terms of x instead of theta. All right, let's look at one last example. Let's look at the cosine of the arctangent of x. And again, we want to write this as an algebraic expression. So again, we're going to start by looking at the inside function, that inverse trig function, and rewrite it in terms of theta. So setting up our triangle, we can see that our opposite side is going to be x and our adjacent side is going to be 1. And then from there, we can find the third side using, again, the Pythagorean theorem. So we'll see that's going to be square root of 1 plus x squared. Now that we have all three sides, we can go ahead and find the cosine of the angle. And again, from there, we can simplify that and put it back in terms of x instead of the angle theta. So there's our composition rewritten in terms of an algebraic expression of x.